Pete Schwartz here. My students gave this presentation about insulated solar electric cooking in spring of 2025, but I'm going to do the introduction. The world's poor still cook on these three stone fires that have environmental, financial, and mostly health implications. For the past decade, we've been developing insulated solar electric cooking, where a solar panel directly connected to a resistive heater inside of an insulated chamber heats food. The reason we like this is because it's healthy, it's inexpensive, and it's easy to use. Lastly, it's simple enough, we hope we can make it locally in Africa, for instance. So we're going to talk about what is ISEC, how we use concrete to make the construction, how we can store energy not just in a battery but also in a big chunk of aluminum, and how we can optimize the power with a simple circuit we've developed. This is a model that was built by a collaborator in Nepal. It has a very thin layer of stainless steel on the top and here as well, and so very little heat is conducted away from the cook pot to the outer shell. The cook pot itself is surrounded by insulation, and there's a resistive heater that's connected to the solar panel, and there's a large piece of aluminum or some other metal or something else that stores the heat so that you could actually cook with very high power, or you can also cook after dark. We call this the nest, where the cook pot sits in the nest and the nest separates the insulation from the food.
Needed to actually effectively cook your food. So we looked into this past summer replacing the stainless steel with concrete. You can see we utilized a stainless steel mesh. This created a composite for the concrete that was able to have us go down to 7 millimeters thin. Concrete is normally not utilized at this thin of a thickness, and we were able to have pretty good structural and material properties from that. We went for this because it was able to mimic the heat capacity of our thin stainless steel, which is at 0.5 millimeter. So in the end, we were able to produce the nest out of this concrete, and it was able to hold one whole David worth of weight. It was really strong, even at 7 millimeters thick. That's attributed to the composite structure that we utilized and the processing. We utilized a lot of vibration to get out air bubbles and increase the density of the concrete, which helped the thermal properties as well as the mechanical properties.
So if you want to cook at anything other than a low simmer with the relatively low power you're getting out of the solar panel, you're going to need a way to store that energy. Now, in an ideal world, we would use a battery because, it's a battery, it's good at storing energy. But we wanted a cheap and local manufacturable solution. So we chose to use a solid thermal storage. So basically, it's just a large mass of aluminum that gets heated up throughout the day. And at the end of the day, when you're cooking dinner, you can use it to cook your food and you can do a sear. So we chose aluminum due to its unique combination of specific heat and thermal conductivity. As you can see here, it outclasses iron in both of these categories. So here's a photo of our solid thermal storage. That was a kind of a bad pour, but it's really helpful to see where everything comes together. So we're going to put the cook pot inside the solid thermal storage, and then this is, again, a photo of the ISEC. This is what it all looks like together. So how we tested it is we would pour in a liter, once it's heated up throughout the day, we would pour in a liter of water and wait for it to get almost to a boil, throw in a second liter of water, and then do the same thing with the third liter of water. And what this does is it gets all the energy from the solid thermal storage into heating up the water, which is easily measurable. So we were able to measure the power output. So for the first 2 liters, we got around 600 watts, and then the third liter, we got around half that, which is plenty to cook what you need. We experimented with concrete because aluminum in a lot of these developing countries is unfortunately toxic. There's a lot of recycled car parts that get used for the production of aluminum, and there's no quality control. So there's a lot of heavy metal contamination of lead and cadmium. So we looked into using concrete because of it's really cheap, and it's around similar specific heat and density as the aluminum. We tried a couple things to increase the thermal conductivity, like sinking iron rods through it, and then we tested it. But at the end of the day, it's just not conductive enough for our purposes. So here's the final result. We were able to sear a good chicken. This is a meal that Eli and I made. It was pretty good.
All right, Alright, so shifting gears to another branch of our research, which is the solar power optimization. So the ISEC reduces down to a circuit that's just a solar panel connected directly to a 100 or a 3 ohm resistive load. The problem with this, which is what you can see on this lower image here, is that a resistor directly connected to a solar panel incurs quadratic power losses with decreases in irradiance, which is like power that you're getting from the sun. This happens because the red resistor line, that's the load line of the resistor, changes the effective operating point of the solar panel. On the power versus voltage curve over there, if you just directly connected a solar panel to the resistive load, you would get those red circles. Those are relatively low power outputs. The goal of our research was to get to those blue circles that you see over there. Those are only linear power losses with linear decreases in irradiance. So we'll talk about how we did that. This is our solution. It's a low-cost solution. The goal of this was that it would be locally manufacturable, simple enough that most people could understand it, and yeah, really cheap. The circuit only uses 13 components. It costs around $2 to manufacture, potentially less using like a PCB mass-produced. But and that's opposed to about $30 for a on-market, low-end, maximum power optimizer that uses a microcontroller. So the circuit functions. The comparator takes in a set voltage, which is predetermined based on what we're using. For our case, it's a 100-watt solar panel, so we use 17 volts. And then the circuit rapidly disconnects and disconnects to the load. This changes the duty cycle of your power output. And then the capacitor charges when the load is decreased. This provides more current on the subsequent reconnection. So what this is doing is changing the duty cycle of your output, which is effectively increasing the resistance. Could you go back to the last slide? Yeah. So what that's doing is moving this load line over here so that you're functioning at these blue points. Next slide. So here's an example of what we saw on an oscilloscope. This is the output of the circuit to the resistive load. This is about a 90% duty cycle at 15.56 volts, which was our set voltage in this case. And yeah, so this means that the power output would be about 90 watts or 90% of the maximum power, as opposed to without direct connection, maybe around 80 watts in this case. And the same would happen for any lower irradiance input to the solar panel. If you have 500 watts per meter squared, which is like about half of your ideal irradiance, you would have a 50% duty cycle.
So, as we all know, the cost of batteries is getting cheaper and cheaper. So, ideally, we're going to move away from solid thermal storage because batteries will be really accessible in these developing nations. So, maybe with our cooker, we could have a integrated home grid system. But this is where the research is moving, is using batteries to store the energy.
Yeah, so a few takeaways from what we researched was that the concrete is a viable solution for structural components of the ISEC. We think that further research could go into forming the outer shell as well, because that's the only major structural component left. It's super accessible, super cheap, very optimized for our goals. The solid thermal storage is a cheap and effective way to sear food and store that energy for fast power transfer. Even with batteries, we do feel that it would be worth having maintaining a small bit of mass so that you can really have that fast and immediate power transfer to really sear your food and optimize that kind of good crust.
What a great diversity. Are there any questions? Yeah, in the back, please.
Is concrete readily available throughout the world?
Yes. Yeah. Concrete's one of the most globally available materials.
How heavy is that?
I don't know off the top of my head the exact mass, but it is. Well, the thermal storage itself is 8 kilograms. Are you asking about the mass of the entire system?
Yeah, so
you can lift it
on
up.
You
You
would
can.
be like a
It's portable.
stove that you put somewhere and that's where they cook, or is that
Yeah.
movable?
It's movable. We lift it up and move it. Initially, we started doing cooking on the lawn over in engineering. We would take it out of our shop, move it. It's probably about 20 pounds. It's not that hard to lift and move. We then put solar panels on the top of Bonderson, so we didn't have to move it back and forth, and we could do our testing in there. But at the end of the day, it is completely, it can be moved and utilized. And the concrete's not that heavy at the end of the day, but it does increase the mass from the, yeah, 5 millimeters is our goal. We got it down to 7 millimeters. Yeah.
How many people can you cook for?
This past summer we were cooking for about 7 to 8 people.
In one of those?
Mm-hmm. Yeah, at once. We would cook chicken, pasta, we made tacos. We really didn't have anything that we weren't able to cook. Anything that you could cook on the stove, you could cook here pretty easily. One of the things is that you just want to throw in things that you want to get that sear first, and then make your way to those like less time, like vegetables or rice.
And how long did it take to cook that?
About 40 minutes. Yeah, so it was fun because we would come, we'd meet every Thursday, we'd heat it up, we'd start in the morning at about 8, and then by about noon we would have the thermal energy stored in our solid thermal storage to where we could throw down our meat, get a good sear on our protein, and then throw in our vegetables about 15, 20 minutes later, follow it up with noodles or rice and some sort of carb to get a full.
So you're saying about 4 or 5 hours to get the heat back?
Yeah, because we had to wait for the sun to come up.
Yeah.
So, yeah. And then we had to use that energy to then heat up the solid thermal storage.
That's impressive.
Yeah, it's really fun. Thank you. Yeah.
So, for the solar panels, what's like a minimum wattage you need to do this for those, and what is the cost of the solar panel itself?
Yeah, we were using a 100-watt solar panel, which is what's typically used with this cooker. Cost of solar panel has decreased significantly in the last like 5-10 years, thanks to like production efforts in Asia specifically. So a 100-watt panel can cost around like $50 to $100 depending on where you buy it and in how much pull. Like buying one panel is pretty expensive, but if you buy like 100 panels, it's about $50 per 100 watts.
The prices come down, and it's largely dependent on where you buy it and the tariffs. So I know a guy selling a 100-watt panel for $12 now in Malawi, where they don't have the tariffs. So they're pretty inexpensive.
The tariffs are typically more expensive than the cost of manufacturing, significantly. Yeah.
We'll do one more in the back.
Yeah.
Do you have a goal for the total cost of the system, or not?
Our goal is to keep bringing it down. As long as we're making forward progress, we're heading the right direction. And solar panels and batteries are both drastically decreasing, and they will continue to do so until they eventually plateau. And as long as we keep trying to convert from metals to concrete, we'll be cutting costs drastically. But aluminum is also really cheap and readily available in these communities, so it's a pretty, between its material properties and its cost and availability, it's a great material for this.
Except for the toxicity.
Difficult to
Except for that. If it's clean, it's good. If it's not clean, not good.
Wonderful, thank you so much.